Hi, this short video is going to cover the creation of this model in PowerPad, and we will analyze it, design the steel members, design the connections, and design the foundations, all inside PowerPad Plus. So if I just come out of the software for a second, all the way, and start the MasterSeries, I'm going to start just as a PowerPad user and take a brand new file in master frame, which is part of PowerPad, and we'll just go into the PowerPad directory and we'll save it as a new file called ppframe and create new. So here we come with the basic preprocessor, and we could use the subframe or the multi-frame to start this off with for us, but we're not going to. We're going to do this all from scratch to show you how easy it is to do it from scratch. So snap grid, put it in the front view. I'm going to do the columns first, so I'm going to choose a UC default column, and we'll come down to say the 23, and we will start at the bottom and we'll come up 7.5 meters, and then turning on my node points so I can see them and making them slightly larger. There we go. I can now do another one that is 5 meters, and I don't have to go like that. I can go 5, 0.00, or input the coordinates on distances just like an AutoCAD. And I'll do the same at an 8 meter off center. So I'm just going to hover here and come across exactly 8 meters, type it in, it's quicker, and I will notice I automatically get a snap to the horizontal above that and to there. So now I'm going to put into beam sections. So UBs, very simply, we're going to choose a 406 by 46 initially, and we will pin the two ends of the member. So we'll make it span from here to here and from here to here. And then we'll create some bracing members, and I'm going to come along and choose so I'm going to go for an equal angle and use the British angles, and come down to a 70 by 70 by 10. So I'm going to make it releasing. I'm going to make it tension only as well. So I'm going to do cross bracing, but I'm not going to put it node to node. I'm going to give myself a wee bit of room. So what I'm going to do is I'm going to come down 500. So just zoom in, and then I'm going to come up 500. So it's more realistic, because normally they aren't connected exactly at that. So those two are in, and I then just close that, and I don't need the node points anymore. Turn on my 3D, and I'll see my basic profile. And if I ask the color by section, you'll see the 3 different section types that we have used, and we could even ask for a legend on those if we wanted to, just to confirm that they are all default sections and they're all 355. So now I want to put some loading onto it, and we go to loads and member loading. This is a plain frame, we're not using area loading, so we just go here, just get rid of that little key diagram, and I'm going to put onto this 2 UDLs plus 2 point loads. So the first UDL is going to be a dead load of say 5 kilonewtons per meter run. The second one's going to be a live, so L, and it's going to be 10. And then going to have 2 live point loads of 5 kilonewtons each at 3 meters and 7 meters. And if I want to, I can see those on the frame by asking it just to draw the loads, and I'm going to ask for all loading cases and just minimize that, so we can see our nice little pretty diagram with our point loads and our line loads on it. So at 3 meters and 7 meters, so off to one side on the frame. I'm now going to go up to my upper level, and I'm going to put in 2 new UDLs. I'm going to put a dead again of 5, but this time I'm going to put in the live as 10. In fact, I think I possibly did the bottom one wrong. That should have been 5 and 12. The live load was a bit higher there. And yeah, that's fine. So there we go. There's my basic loading. I need to get some nodal loads on to the two ends of the members, and I can put those on directly as end of member loads here, but it's better to put those on as nodal loading. So nodal loading, and I'm going to choose this point, and I'm going to have it as a wind 1 load in the x-axis, and I'm going to make that 10 kilonewtons. And then I'm going to add another one, so second group, and it's not this node or that one, it's this node up here. In this case I'm going to make it 5 kilonewtons. So we have these two nodal point loads coming in, so 5 there and 10 down there. And if we just scale up, we should see those. It doesn't show those both at the same time, it only shows the one I'm interested in. So that's very simple, very, very quick to do. And I'm just going to close that down. Or no need to close down, just go to the next function. The next function you want to look at is putting some supports in. So releases, member end releases, static supports. So I'm going to put in a pin support here and a pin support here. I'm just going to turn off the load diagram because I don't really need the loads anymore. There we go. So two little pin supports. If I look at my member end releases, we will see that we've got pins here, here, and here, and here, and here, and here. Oh, don't need that there. And that's all I need to do. My last thing I want to do is look at the loading combinations. So loads, loading cases. I can create those manually, or I can just go into auto and say, right, for dead plus live, I want ultimate and service to 610A and B, and I want notional load at 0 and 180. So plus and minus. Live load only is useful, dead load only is useful as well. Dead plus live leading, and dead plus live with the live leading, and dead plus wind favourable and unfavourable, and in case somebody wants it, the wind load only. So I'm just going to add all those in, replace the existing loads, and analyze my frame. Static analysis, very straightforward. You can see notional horizontal loads added as a plane frame, and walking across, I now am into results, graphical results, and we can turn off the 3D and we can turn off the fancy coloring. So it's just a simple black and white in front view. There we go. So bending moment diagrams, as you would expect under the dead plus live, we get our normal deflections or diagrams. As we move over to dead plus live plus notional, because these diagonals were tension only, it's taking this one into effect, and it's not taking this one that went into compression, so it's taking the load in this one, and it's not a large load. And then we get into the wind only, and we can see the higher and higher loading building, and that's actually the moment. So if I actually go to axial, we'll see the 14 and the 42 kilonewtons coming in as our bracing loads. And we can see our deflected shapes as you would expect. It's sort of like a propped cantilever because this brace holds this all in place here, and then the top half cantilevers out. So the cantilever is much more onerous than the first part, but it's fine. We could make things better by making that a fixed connection, and that would be easily done. In my case, it's all pinned. So let's go and design it. And what I'm going to do first of all is I'm going to set up some rules for the design. I'm going to tell it I want to do an axial moment on columns. So let's label it up. and I want to apply this and this and this and this all as one column, as 4 different columns, 1L, and keep them all the same section size. And then going to add in another one for the 2 braces, and these will in fact be strut and tie. And because it's angles we're choosing, we really should think about holes. So we're going to have one number 22 hole, and just play safe, put it into both the web and the flange, and everything else is fine. And then add in, and that's brace, always helps me put a name in. Add another one in, and this is first beam, and it's going to be this member, and it's going to be 1L, so unrestrained, or it could be fully restrained. Let's go for fully restrained. Whatever's sitting up here is going to be restraining it. And then we want to do the other member up here, but this will be unrestrained, lighter load and unrestrained. Because it's only one member, we don't need to tell it to change the data for the whole group. So here we go, and we go into our design, steel member design, and we'll find we've automatically got our design checks, and we'll see that we're getting our loading here. So our axial with moment on the first portion, on the second portion. So the upper portions are okay, the lower portions are a wee bit, because of this moment coming in here with the push-pull and everything, a wee bit unhappy. So 152, let's change that to 30, no good. A 37, not very good, still getting there. And a 44, but for the same benefit we could get a far more robust 46, easily obtainable UC, and if we then just check that, it works for all 4 of those. Our bracing members coming along, 70 by 70 by 10 angle is working for this one and for this one. My upper beam, sorry, my lower beam is failing on deflection. At the minute it's taking 1/360, the default deflection. I'm going to come along and change that to 1 in 1. What that means is I'm going to use a table where I'm telling it 360 live but 250 dead plus live. And now the section works, fully restrained, and if I ask it to auto size, so walking down we'll see that we can see the section's not working. If I sort by weight order, I'll get a more optimum result. And there we go, 457, 152, 50 is working. And if I move up to the top member, which is more onerous because it's unrestrained over its full length, again we'll go for the 1 in 250 for deflections. Back to here, and we will try and find that it's a 406, 147 by 74 is the first light section that works. So we've chosen our new sections. Always important to reanalyze with the new sections and then to re-scan for any failures, and we'll find that nothing is failing, everything is perfectly good. Now we've got our frame designed. If we're worried about P delta analysis, we would have to consider lateral torsional elastic critical load factor, which is throwing up alarm bells and telling me that I do have problems with the structure. So it's very flexible. Just coming back out as part of the design process and going into second order, I'm going to ask it to do a P delta analysis. And I could argue that it's geometric stiffness matrix method because it's a multi-story rather than braced rather than unbraced type frame. And then I'm going to apply that. I'm going to just say put it on all ultimate cases and apply. So if I now go analyze static, you'll see P delta is applied, plane frame, And of course we do find that it's unstable because it's just too flexible. DX on node 10, and I say no. Up here it's just moving. Remember, if we had this curvature. So what I'm going to do, very simply, is I'm going to go and remove the end restraints here, make this a fully fixed up here. Down here will be okay. And reanalyze static analysis. And we should find that it's still a wee bit flexible. I need to possibly increase those sections before I go on to make this work under second order processes. So properties, sections, take these and change them to be the 60 kilograms, and that's going to have that effect on all of these. And bear in mind we're still pinned here. What we're going to do is we're going to turn around and take off these so it's a portalized and braced frame, and analyze static. Here we go, and back into design, steel member design. We'll find the columns all work. The beams now work a lot better. We could get away with lighter sections. So sorting by weight order, we could come down to something a lot lighter. So I'm going to say the 406. The beam here, we could also get away with something possibly around the 406. It's not working. Let's move up slowly. And the 35652, and scan for failures again. And we'll find that my revised section sizes all now work. So that's my sections done. And also, if I look at the last design check, that last one, it's happy because we have notional loads and done to the structure and say yes. Now if we go in and look at the connection design, again, all part of the same PowerPad program. I'll just accept the default, but will not have any brace tie forces. Beam to column flange, yep, we're going to have one of those. And it's going to ask us where. I'm going to do this one first, just there, and we will see that the default with 3 bolts in works. And I can just scan through the cases and see yes, that works. And we'll just check it on the other side, apply to the other side, and scan, and that works. Add another joint. In fact, what we'll do is we'll copy this one, and then we will apply it to the upper member. And again, similar configuration, just scan for failures. Everything's okay. Let's pull this up, add a third joint. It's a base plate, and we'll add that down there because the wind was pushing in that direction, so it's a more onerous. And with the default slab base plate, do we need to enlarge it? No, we don't, so we wouldn't need to enlarge it. And if we apply that to that member instead, and then just scan, there's no problem there either. So finally, the bracing. And if I add in another one, and we go to our bracing members, and we're doing vertical bracing to a column, and say OK, and it's going to say where, and I'm going to say here, and we will see that we just need to get the bolts right. The bolts are not right, so click on the bolts. I'm going to say 1 column of bolts down the middle. Everything's fine. Everything works nice and neat. We can also turn around and say no, we don't want a knuckle. We'd prefer to have a tapered straight or a triangle, which is quite nice and neat, and have that all sorted out and done quite neat. And that is all your connections done. So frame analysis, steel design, connection design. Last thing to design is concrete pads. We're going to go for C3240 concrete, and safe working pressure, we're going to go for 200 Newton, and we'll have no additional, we'll be buried 500 below ground. You'll find that 1300 square by 450 will work for that pad, and for this pad it's slightly less. I'm going to ask it to resize it, and I'm going to make them both the same, so 1350 by 450, and I'm going to make this one 1350 by 450. So that's a quick 20-minute tour around PowerPad doing a full steel design on a frame, doing this analysis, the connections, the steel member design, the bracing design, and your pad foundations.